Okay, let's return to Wigner's friend. So after you have now a lot of familiar with that from Ile's lecture and also from yesterday, I just wanted to remind you of a few points which are actually different from what you just have heard, just to make sure there is no confusion. So you have now seen there's a huge variety of Wigner's friend type experiments and extended Wigner's friend experiment, and there were different assumptions. Now, in this last lecture about that part, I would focus on the version that I had presented with Daniela Frauchiger, which makes a particular assumption, which is in a sense quite different from the way of thinking from what we have heard. And I just wanted to briefly point out this difference. So the main difference is actually the role of agents. As I pointed out yesterday, in the approach that I'm taking, an agent is a user of quantum theory. And we are applying quantum theory always from that agent's viewpoint. And there are, of course, several agents, and the assumption on the universality or the universal usability of quantum theory is that all of these agents are equally allowed to apply quantum theory. And this is in contrast to something that you see very often, not only in the discussion of Wigner's friend, but generally in physics, that one says, let's just look at the system from the outside, which is very natural. This is kind of how we grow up in physics. Like if you look at the classical theories, we always look at, in a sense, the universe from the outside and have these laws. And we think of a hypothetical kind of viewpoint that doesn't actually exist, in the sense that there is not necessarily an agent there. That's why I called it yesterday the God's viewpoint. And this is something that is important to keep in mind. So whenever I make a statement today, when I say, now we apply quantum theory to that, it's actually one of the agents' viewpoints that is taken who applies quantum theory. And by actually making the assumption that all these agents are eligible to apply quantum theory, we can replace, or in a sense this replaces other assumptions which enter the other no-go theorem. So in that sense, it's a rather strong assumption. So in particular, just again to avoid kind of potential confusion or to separate it from the other things you have heard, there's, for example, no free choice or no locality assumption. There's also no assumption of absoluteness of observed events, but as Ile pointed out, it will be replaced by the consistency assumption. So the assumption that I'm using, therefore, to summarize this short introduction is the assumption that I called Q, which is the universal applicability of quantum theory, and the assumption C, which you will see in action today. So if you don't remember precisely what it was, you will see it again shortly. So that's the thing, but let me now briefly start with a review of two things. So at the very end, I introduced a technique that I called quantum whispering. I will review it in a few minutes, but I want to start just with the more general picture. And this picture has now also evolved. I had a very nice discussion with Rob Speckens yesterday, also over lunch, about that. And so that's a brief review of what is the big question that we are answering here. And so maybe you remember I started by saying there could be a system, S, that we are interested in. And this system is maybe measured. There's a measurement device. And the measurement device shows a result, let's say Z. And now we could look at that system. So actually, as I'm drawing that, I'm also taking a perspective. So I'm maybe an agent rather far outside. And that now I see another agent, Alice, here inside. And this agent is measuring the system. And now I talked, or maybe you also remember, that I mentioned this notion of a Heisenberg cut. So this agent, Alice, has to decide which system she's going to describe as a quantum system. And one choice that she could make is to say she just describes this system S as a quantum system. So I enclose it with a dotted line. The dotted line is now the Heisenberg cut that Alice chose. Now there could be a different observer. Let's say, I think it was Charlie. And Charlie could choose this cut differently. Charlie could say, oh, this is a measurement device here. A measurement device is itself a physical object, so let's also apply quantum theory to that object. And Charlie would therefore apply quantum theory to these things jointly. Now, what I mentioned is that von Neumann famously proved that the predictions that Alice and Charlie are going to make will be the same, provided they look at the same result. So here in this picture, Charlie would also try to see, or would see the results, or maybe I indicate this like this. So Alice has seen the result set, Charlie sees that result set as well. I mean, this would mean more precisely that he has an additional measurement device outside of the cut. For example, he could treat Alice's eyes as the measurement device and just ask Alice what was the result. That's a possibility.
Those are meant to be different colors. You can't really see them.
Yeah, no, there are not so many choices. I will need a third. Well, yes, there is no green left. Yes, I have a red, but I reserved it now for the next observer. So, yeah, so let's just therefore label these people. So, now what actually what Rob Speckens told me is that he would typically in his presentations call this result that I attributed to von Neumann, and is by von Neumann, he would call that the motility of the cut. And what he means, what he would say here, and I mean, I also think this is a good way to phrase it, but it then would also tell us where the differences is to what we are going to do, is that if, for example, Alice now assigns a state to the system S, so her knowledge, if you take an epistemic viewpoint, is captured by a quantum state, then if Alice and Charlie have seen the same information, so they have seen what the value of that measurement is, then they would assign the same state to this. So we have actually an equality, or I mean, there could be different maybe reference systems, but there is at least a one-to-one relation between the state assignments. So one could call that the motility of Heisenberg cut. But this is not what we are exploring with the Wigner's-Friend experiment. With the Wigner's-Friend experiment, we kind of take this to an extreme that is not captured by von Neumann's result. And the extreme is the following. We have here another agent, Bob. And Bob treats the system S, the measurement devices, as well as the agents, Alice and Charlie, as quantum systems. And so I draw this now deliberately as a square box here, more or less, because you could imagine that they are placed in an isolated lab, and Bob just describes this whole lab, including all the content, so therefore also Alice and Charlie, as a huge quantum system. But because it's isolated, he fundamentally has no access to the value set that is measured. This is now important. So Bob has different information, I mean different in the sense, in this case, just less information about the system, which, by the way, is sometimes a bit counterintuitive. When I mentioned at the beginning, we are used in physics to take this outside viewpoint, and in classical physics, if you look at things from outside, we usually assume there is this viewpoint where we could, in principle, know everything. We know, like in classical mechanics, we have this idea that, in principle, one could know the position and momentum of all mass particles and maybe the whole electromagnetic field and so on. So here, if I say Bob stays outside of this box, he fundamentally has no access to the measurement result that Alice and Charlie has seen. So in a strict sense, Bob doesn't have that information. It doesn't mean he has less information, because he has other information that Alice and Charlie don't have. For example, he has a description of Alice and Charlie as a quantum system. So the information that Bob has is not directly comparable in the sense that it's more or less than Alice. There is no order relation, but they're talking, so the intuition is they talk about the same thing. So what we want is still that if we now ask ourselves, what is Bob's knowledge? So then, of course, it's different knowledge. And so a minimum requirement that is reasonable is that we want Bob not to contradict a statement that Charlie makes about an observable value. Yes?
Doesn't Bob know that Charlie measured Z? So isn't it more information?
So Bob knows, let's say Bob knows what Alice and Charlie are doing inside, but he doesn't know the actual value set. He just knows there was Alice and Charlie measure the value, and they have this stored in their brain, but he doesn't know the actual value.
Maybe the question, Z is not the measurement basis, it's the outcome.
Aha, sorry, yes, I should clarify. So Z is the value. So maybe I could here indicate that in the example, this is now a view not from outside, because we wouldn't know that, but this is kind of a pictorial thing. The measurement device could have shown Z is equal to 1. Okay, now these pens are running out of color. So, and now also Alice knows Z was equal to 1, Charlie knows Z is equal to 1. Now Bob knows Z was measured, but he doesn't know whether it's 0 or 1. That's the idea, because it's in an isolated box. I'm not saying something, I'm just saying if someone is in a perfectly isolated box and does an experiment, you don't know the outcome. I'm just saying that. Or did you mean something? Maybe I misunderstood your question.
What is then the hierarchy of knowledge? There's like two different kinds of knowledge, right?
I mean, my point is there is no order. So if you look at the different knowledge that agents have, there is no there's no full order between the different knowledge. So in that sense, there is no hierarchy, if you mean an order relation between the different knowledge one can have. Now, let's suppose, for example, the system S was somehow correlated to something else, some other system Q that could be measured, and maybe here it gives the value X. Now, let's suppose Charlie makes now, and let's suppose this is now also within the Heisenberg cut of Charlie and Alice, so they can all talk about X. Then it could be that Charlie makes a statement, so let's put that into a second bubble. For example, he makes a prediction that X is equal to 1. Let's suppose he assigns probability 1 to that. So he says, I'm certain X is going to be 1. So then what we want to avoid at least, and this is just repeating what I said, what I would consider a paradox, is the situation where Bob would now at the same time assign the value 0 to that. That would be, that I want to avoid. Or in other words, I require a compatibility, not an equality of knowledge, but a compatibility. And so one could even think of many compatibility requirements. For example, equality like this is also a compatibility requirement, but a very strong one. And now I'm kind of going to the weakest one. I'm saying I'm considering the knowledge of Charlie and Bob compatible as long as it's not the case that they are really making contradictory statements about an observable value. For example, that would now be considered a contradiction. That's what I meant last time when I talked about the paradox. But you see, already here, when I say that, I need to I have implicitly used this assumption C, because I could a priori say, okay, Charlie means by X equal 1 something and Bob something else. Maybe this should not be compared. So now, what you may remember, just also to repeat that assumption, is that if Bob also knows that Charlie knows that, so I could kind of put here a huge bubble. So, for example, Charlie could tell Bob, I've seen X equal to 1. Then we could now apply what I called assumption C, the consistency assumption that Ili also mentioned. And assumption C would tell Bob, if I know that Charlie assigns the value X, 1 to the value X, then I should also do that. So the assumption C means there's another, let's say, thought he has. So the red things are all thoughts by Bob. And so his thought by assumption C should be X equal to 1. And now we really have a contradiction, because now in this experiment I told you Bob somehow derived X is equal to 0, but now reasoning via Charlie, he also arrived at the conclusion that X is equal to 1. And this is now what I call a paradox. And what I'm going to show you now in this hour is that we can indeed arrive at such a paradox using just this assumption C plus the universal validity of quantum theory. So that's the goal. Is that clear? Because if yes, then I would start with the argument. There's a question.
Can you explain what a paradox is? Because if Bob has access to different information, that you will derive different results.
Yes, so, okay, that's a good point. So you're saying, maybe I shouldn't be worried about that because Bob has access to different information. that's true. I should be more precise and say what we are actually now doing is to say, we consider an experiment where the initial knowledge of all involved agents is identical. So they're all informed about what's the experiment. So in a sense, I describe the experiment and then I attribute roles. I say, you are now in the role of Alice, you are Bob, you're Charlie, and you're the referee, for example, in this game. So everyone has the same initial knowledge, but the only difference is during the experiment they see different measurement devices. Like, for example, here, if you imagine this situation, there is Alice now is in this box. They started with the same knowledge, but now Alice is allowed to see this outcome, whereas Bob is not allowed to see that. And here we wouldn't want to arrive at the contradiction. It would be as if, let's say, I have usually this example of a coin flip when I try to explain the subjective nature of probabilities. If I flip a coin, put it here on my hand and look at it and ask you what's the value of the coin, is it heads or tails? You would probably say it's 50% heads, 50% tails. I would say it's certainly heads because I look at it and see it. This is not a contradiction because, I mean, we have different knowledge now, but your statement is not contradictory. You're just saying it could be heads, and I'm saying, yes, it's actually heads. It would be a contradiction if you would look at something else, you would look at out of the window and infer from that, actually the coin will be tails, and then tell me, I'm sure it's tails. Then we would say, we are in the same world, we started with the same initial knowledge, I looked at something, you looked at something else, and suddenly we are in a contradiction. So that's what I want to avoid. And why do I want to avoid it? Because this is really something we could, like, we are here thinking of thought experiments, but a thought experiment is an experiment that in principle we can do if we had the technology. And of course, we make a prediction about, so I was pointing out, we are not making a prediction about something abstract like a state. We are making a prediction about something that can be verified by an agent at the end. It's one agent, it's Bob, who could actually run the experiment and put all this knowledge together and check which is now the right thing. He would either observe x equals 0 and x equal 1, and therefore he could decide which of his reasoning chains was wrong. So it's really pointing to a flaw in the theory, in that sense. So we know this theory cannot be a good predictive theory, because if we carry out the experiment, it will fail. Okay, let me now, or are there any other questions? So, as I said, this is the goal. Just to say, in standard quantum theory, with this universality requirement, we get into this contradiction. And I hope you understand why I find this very worrying. I will not present you a solution. I don't have a solution. And I just think this is an actual open question, how to correctly apply quantum theory to a multi-agent setup without giving up our ability to collaborate, which would mean to give up this assumption that I called C. Okay, so that's the starting point. Let's now go to the technical thing. And for that, I return to this quantum whispering idea. And I will just present it again from the scratch in a sense, but go a bit fast. But please stop me if there is a question. Okay, this pen is also no longer good. So let's imagine the following situation. There is an agent, Charlie, in a box. Charlie is receiving a qubit from the outside, and now the notation, the notation may not exactly match what I said yesterday, because I will already use the one that will directly lead to the paradox. So Charlie receives a qubit R, measures it in the set basis, and gets an outcome, and I will denote the outcome by set hat. The reason I call it set hat is we will later return to this so-called complementarity game that I introduced to you yesterday. And there, remember, the task in the game is you give to the referee a qubit, and you also provide to the referee two predictions, one called z hat and one called x hat, which should be the values that the referee would measure if he measures in the z basis or in the x basis. So z hat would be that guess. So that's just the reason for this notation. You don't need to worry otherwise about that. For now, we will return to that. Now, Charlie wants to communicate that value to the outside. So we assume he can send one qubit here to the outside world. And he now prepares the qubit according to the following rule. if z is equal to 0, he sets the state phi of the qubit to 0. If z is equal to 1, then he sets the state of the qubit to 0 bar. 0 bar is just the equal superposition of 0 and 1. Now, that's a communication to the outside. Let's now suppose we are the outside. At the outside, we receive this qubit and we want to make sense of it. One option for us is to measure this qubit in the set basis and get an outcome, and I will call this outcome U. Now, what can we say? And that's what I already explained yesterday. This is just a repetition, but you can easily reconstruct it. If U is equal to 0, what do we know about the value of z hat? Does anyone remember, or does anyone see that? I think it's immediately visible. Yes? 0. Not necessarily. So if U is 0, this means there was an overlap of that state with 0. But both this state, which is 0, has obviously an overlap with 0, but also 0 bar. So 0 bar is 0 plus 1, has also an overlap with 0, so it could have been both. So actually, we don't know in this case. Let's just do something else. I mean, I could also consider the outcome where U is equal to 1, but I don't want to do that. I want to look at something else. I want to ask what happens if we measure it in the x basis, and let's suppose we get here an outcome that I call W, and this W is equal to 1 bar. So 1 bar is the complement to that. So maybe just to be complete, 1 bar is the state 0 minus 1. And the important thing, this is orthogonal to 0 bar. What can we say now? So W is 1 bar. What is the conclusion we can make about z hat? 0, right. Why? Because 1 bar is orthogonal to 0 bar, so it couldn't have been z equal to 1. And of course, as I said before, all the agents know the protocol. So we know Charlie either had 0 or 1. So if it was not 1, it must have been 0. Okay, so that's what I call quantum whispering, because you see, it's kind of an asymmetric communication in the sense that only for one particular value, I mean, there are more possibilities. I just consider those that are later relevant, but only for certain received values can we infer what he wanted to tell us, or what Charlie wanted to tell us. I think there was a question somewhere here. Yes?
Can we not assign, like in the case of U0, that it was like, I don't know, 50% Z was 0 and to, I don't know, 1 divided by, I don't know.
Yeah, I know what you want to say. You want to say you can still make a probabilistic statement. You could, but here in the way I presented, you're missing some important information. You would need to know how likely are these sets in the first place. So if I gave you a prior distribution over this R, then this would be correct. You could make some probabilistic statements.
This can be part of a protocol, right?
Yes, yes, right. So I will actually do that. So indeed, when I say here nothing, this could also mean that if you have some probabilistic information that you say, oh, I still know with that probability this happens. That's absolutely correct, yes. Okay, now let's indeed do that. So what I'm now going to do is to present the actual protocol, which is now a revised version of this protocol I developed with Daniela Frauchiger, and this revision is due to Ladina, who is also here. So this revised version, the basic idea is it's almost the same as the original one, but we bring it in contact with this so-called complementarity game. So the goal is not to immediately have a paradox, but to say, first, we can win this complementarity game. And actually, the reason why we are phrasing it in that way has to do with the fact that our goal was to make this paradox very analogous to paradoxes that appear in black holes, for example, the firewall paradox. And with this reformulation, we can make it almost analogous. Okay, so what I'm now going to do is to draw the same thing almost, but make some variation. So the first variation has to do with precisely your question. I'm actually now saying how is this state at the input prepared, and I'm saying it's a state. I will not put the normalization. That's why I put here this similarity sign. So it's a state which has is a superposition between 0 and square root of 2 times 1, the one state. So that's just one particular state. I can choose it. There's no a priori reason to choose that state. This just turns out to be useful for the analysis. Now, as before, Charlie is in this box and measures the thing in the set basis and calls the outcome set hat. And he applies the same rule. So if it's 0, prepare. I'll just write it like that in short version. So the Q will be like this. If it's 1, then the Q will be in the 0 bar state. So the Q will be sent out to someone else, but now there's a difference here. So here I now assume there is Alice. And Alice measures this in the set basis. So she's here. It's no longer us who measure. And also, now comes a kind of maybe surprising thing to do. I say this Alice who receives that thing is also in a other isolated lab. I can do that. I mean, it's isolated up to the possibility, of course, to inject that particular qubit that I call still Q into her lab. Now comes the thing that you have now seen many times. If I look at the isolated lab from the outside, according to our assumptions, this just evolves according to a unitary evolution U. So what I can do, okay, now there's not so much space here. Let me just do it like this. So time goes downwards, but I bend it a bit. That's a kind of time fold. And so I apply here the inverse of this unitary. And then, of course, I have here, I mean, let's say, maybe I should briefly make a remark that just to make sure there's no confusion. So rather than actually talking about the unitary, it's just much more convenient to think of an isometry. So unitary is in particular an isometry, but an isometry can go to spaces of different sizes. And so I could talk about a unitary by saying, let's also here at the input explicitly write the degree of freedom of everything in the lab as a wire. And then the unitary acts on all these degrees of freedom. But because I'm not actually further interested in the details of this degree of freedom, I can just ignore them from the description. It's just a descriptional thing. There's nothing physically that changes, and say, let's only describe the mapping from this qubit to all these degrees of freedom of the lab, not care about what is actually the state of these degrees of freedom of the lab beforehand. And if I do that, then I look at this reduced mapping, only from this qubit space to L, and that's still an isometry. So this isometry is kind of describing part of the unitary. And I can still revert this isometry, and then I get back the qubit. If I would write it as unitary, I get back also the lab degrees of freedom, which I would just throw away. So it's just for kind of economics of notation. But you can informally think of a unitary going on, and I'm just ignoring these wires that are not relevant. So that was a slightly technical comment, but basically it means don't care about the sizes of these systems. I'm just focusing on the ones that are relevant. And now the total thing from here to here is just an identity, because I've applied an isometry and the inverse of that. So I can now just apply an X measurement and get an outcome, and I call that outcome as before W. So if you compare to what I've done before, just that you see this relation, I've now actually replaced this thing here below, where I said we could either measure in Z or X by some device where both is measured by different agents, namely Alice, who is here in the box. Let me also label her, for the lack of is measuring in Z, and here could be an outside agent, Bob. Oh, Bob was usually red. At least we have the red color. So Bob here is measuring in the W, in the X basis, and has the same conclusion as before. So we could even, now all the things we calculated here, or all the conclusions I've written down here on this piece of paper still apply. It's just the very same situation for the respective. You just have to be careful who makes the concrete statement. Like this one statement is made by Alice. Maybe I write this here. Alice can still, in our new setup, make this statement because she measures in the Z basis, whereas Bob measures in the X basis, and he could make a statement of this type. Otherwise, I have not changed anything. Okay, now we are in this setup, but now I will do some further change. So here in this particular, so this is also a lab, and this lab also evolves unitarily or with an isometry, if you like. But here I keep the lab degrees of freedom explicitly. So here are the lab degrees of freedom. But now the lab is a very large system, so I will again apply an isometry to make this a bit more accessible. So, and this can be done in an easy way. I can say one lab degree of freedom is, I mean, the lab have lots of degrees of freedom, but if I assume that the initial state of the lab was pure, and let's just make this assumption. This assumption is usually made in Wigner's friend experiment. It's actually not a necessary assumption, but it simplifies the presentation here. I could say that if Charlie measured Z equal to 0, then of course this will, and a lot of other degrees of freedom in the lab will also indicate that Z was equal to 0. The measurement device will show Z is 0, Charlie's brain will show Z is 0. So there will be some huge state of the lab, which I call the Z equal 0 state of the lab. And now what I'm doing, I apply an isometry which just sets this huge state on many subsystems back to the state on one single qubit system, which I call S. So what comes in is the lab degree of freedom, what comes out is a system S that is just a qubit. And the other thing this isometry should do, if the lab is in the state corresponding to Charlie having seen outcome 1 here, then it's set back to this qubit being in state 1. We can do that. That's an isometry. I mean, isometry means it preserves a scalar product. Okay. Now, this S is now going to be sent to the referee. So remember, in this game that I introduced last time, the referee's role is just to either measure this qubit in the X basis or in the Z basis. So the referee makes a choice. He either applies a Z measurement or he applies an X measurement, and he gets Z and X here. I mean, either of them, not both, but one of them. So that was, that's now, so the strategy for winning this collaboration game is now the following. So let me again tell you here in this context what the collaboration game is. So Alice, Bob, and Charlie, they now collaborate together. They are one team that plays the game. So remember yesterday I just talked about one player, but they're now a team playing the game. There's also the referee, and the referee, and the game goes like as follows. The team of players has to send to the referee a qubit, S. And then the referee measures it in one of the two bases. But what Alice, Bob, and Charlie also have to do, maybe Bob, who is outside, can take over the actual task. They have to send to the referee a prediction Z hat and X hat. And if this prediction matches the corresponding outcome, they will win the game. So for example, if the referee measures in the Z basis, then he verifies whether this actual value Z equals this prediction Z hat that Bob sent, and if this is the case, they win. So now what I will tell you is that there is a particular prediction they can make that will always win the game. I mean, we'll have to do some additional tricks for that. Actually, let me just start for that. What they have to, yes?
Who is collaborating? Like you said, Bob?
Ah, yes, so the collaborating are all the players with a name. So Alice, Bob, and Charlie are one team, and they are playing, if you want, against the referee. So the referee checks whether they won. Yes?
I have a question of doing an inverse unitary on an agent.
Mm-hmm.
So if you do that on an this exactly the same thing again? Like after the inverse unitary would be this exactly the same state as before the measurement.
Yes.
So the thing to the agent will do is repeat exactly the same thing.
Yes, I mean, okay, that's a question of what do you do after you reverted it. So indeed, the agent degrees of freedom, which are now not drawn here, would be, he would be in the situation before he has carried out the measurement. So he would probably still think, oh, now I need to carry out the measurement, which is actually now a good thing, because precisely the next thing I want to say is, let's now repeat that. And, okay, I mean, at some point you just have to intervene and tell the agent, now we are done. So,
My opinion would be like really would have to repeat itself because it's the same state. That is in the same state, agent is in the same
yes,
state.
but it doesn't prevent, like, it's not that from the outside everything is in the same state. So maybe for you as an agent looks as follows. You think, I haven't measured. Now someone opens the door to the lab and says, actually, you're done. It's already completed. It's like you, if you are in a kind of surgery and get some sleeping thing, and suddenly you're done. You didn't realize anything. You don't remember what happened and so on. I'm not sure it's a pleasant experience or not. That I don't know either. But I'm just saying, I mean, remember what I said. The important thing is an agent is just a computer in our way of things. So it's a machine. So we don't really need to worry about whether this agent now thinks. So the computer is doing its task to do measurement, to make predictions. At some point, someone from the outside, Bob, reverses the whole evolution of the computer. Whatever that, I mean, now we don't need to ask the question, what does the computer perceive? It's just all operations are run in reverse. At the end, it's reverted, and we just, from the outside, stop it. The computer cannot itself, maybe that's the point, the computer cannot itself decide that now it doesn't have to run again. And Bob has to do that and say, now you're done with your job, let's just stop that computer. So I think it helps to think about the computer, because then all the problems of what does it now feel like if you are reverted disappear. And clearly we can run a computer backwards. The computer doesn't mind. I mean, I could do it with my classical computer. I just take the program, I decompose it into the gates. If all the gates are reversible operations, which they are in principle if I have sufficient systems, I run them backwards. That's the idea. So you imagine a circuit, I just run it backwards. So I think it really helps to think of a computer rather than a human. And that's the only thing we need. So we are actually talking about networks of computers that are applying quantum theory. We're not talking about consciousness or anything like that. I mean, let's say I couldn't answer your question about what it means to revert someone in time in terms of what it means for any aspect that humans also have, like perceptions and consciousness, but I can do it for the model we have that we need for this SOT experiment, which is only as an information processing device that applies the rules of quantum theory. Is this okay for the moment? I know there's some discomfort because everything was introduced to model us, but yes.
My opinion should be not a perfect unitary, but something like almost perfect, imperfect. So
Yes. By the way, all this is robust. So if you do everything with a small deviation that is smaller than some small probability, let's say 0.01 or so, then this works. So that's another thing. So the whole experiment is tolerant. Okay, now we can proceed to the final stage. We just need to analyze that. But as I said, we repeat it. And we repeat this thing. So Bob just tells everyone, so now think again of computer, it just reruns the computers until here the value W gives 1 bar. And actually, I will now not do the calculation because you could doubt whether this ever occurs, but the probability of W equal 1 will occur. You can easily verify that. That's not an interesting calculation. And just do that, and only then, so here the order is, you should understand it in a way, we only send it off to the referee once this condition is met. So if this condition is not met, we just restart, do everything, but once this condition is met, we say, now referee, this is the qubit we want to play with. Remember, the game was phrased in that way. We can determine which is the qubit that the referee should measure. So that's important here. So we just keep generating S's until this condition is fulfilled and send that off to the referee. And this will happen after a finite time with certainty. Okay, now comes the final stage of all that. This is quite, so now it's surprisingly short in a sense what we need to do. let's just briefly write down the following. So psi is okay. So I will now write the analysis from from Alice's viewpoint. So maybe it's now useful to still have this diagram in mind. I don't know how to do that precisely. So I have to switch sometimes, or maybe I'll just start here writing. It will be a bit crowded, but so I always do the analysis from someone applying quantum theories viewpoint. So let's take Alice's viewpoint, and Alice could ask herself, what's the state of the system at that point when we are here? So there's a state psi of Q and L. And this is very easy to write down. This is very basic quantum theory. So let's do it with, without the normalization factors. So I do not normalize the state, as here it's also not normalized. I can say, okay, there is on the one hand the Q system. The Q system is in some state, and there is also the L system. And one possibility is that the L system is in this state that I should have called it Z hat equal to 0. What's the state of the Q system if Z hat is in the state 0? The Q system is in the state 0, because that's the rule that Charlie follows. Plus, it could be in, like the Z could be in the 1 state. In that case, Charlie prepared the Q system in the 0 bar state. Now we can just expand it. So remember, 0 bar was 0 plus 1. So I can write this as 0 Q, Z bar equals 0, plus, again, 0 Q, Z hat equal to 1, plus, okay, 1 Q, Z hat equal to 1. So I just expanded this by putting here this. Actually, here I forgot the square root. But the square root of 2 will compensate the fact that here the 0 bar is defined as 1 over square root 0 plus 1. So this was actually the reason why this square root was chosen, to have here an equal superposition of the 3 terms. Now we can read off something interesting from here, because note that this thing, so if we undergo this V, so if I look at the state V applied to psi QL, then I will get a state on Q and S. And what's that state on Q and S? This is now a very simple state. It's 0 on Q here, but Z equals 0 and Z equal 1 is a state corresponding to 0 bar in the S spaces. So I can write this as 0 bar. So this is the only maybe non-trivial thing. So I just said Z equals 0 and Z equal 1. This superposition corresponds as a qubit just in a superposition of 0 plus 1, but 0 plus 1 we called 0 bar. And then I have the second thing, which is just 1 q. Here is again a square root of 2, which is not so relevant, and 1. So we have this state. What can Alice conclude from this? Alice can make the following conclusion, and I will just make a list, and you have to maybe, I will write it here. So Alice can make the following conclusion. If U is equal to 0, so remember, Alice may measure here U, and she may have gotten the outcome 0. If the outcome of U is 0, what can she conclude about the outcome of this measurement in the X spaces? Does anyone see that? That's now a question. So suppose Alice now knows she measured Q, got the outcome 0. What will be the outcome of the referee? Sorry?
0 bar?
Exactly, 0 bar. Because you just read it off. If she has 0, the state of the system S that is going to the referee is 0 bar. So indeed, she can conclude that this measurement X will be 0 bar. So that's Alice's conclusion. And that was actually the most complicated one of all. Now the rest of the calculation is very easy. Let's now look at Charlie. What can Charlie say? Now we can use our knowledge about, I mean, for Charlie, let's make the following assumption. Let's consider the case where he observed z hat equal to 0. What can he say now? So Charlie observed here a 0. What can he say about the outcome of U? What do you think? Does anyone see that? So maybe I'll put this here as a question. So what should I write here? The calculation from before is irrelevant. You just see it from looking at this box. So Charlie measured 0. Does anyone see that? Yes? Yes. He sees 0, or he would indeed say it's 0. Why? Because he just prepared, like if it's 0 here, he prepares the Q in 0, and of course if he prepares it in 0 and someone measures it in the set basis, then it's 0. So that's absolutely correct. Now comes the interesting step. Now Charlie can think about Alice. So Charlie knows now that it's Alice who observed U equals 0. So to be more precise, actually that's what this means in a sense, is that Charlie now knows that Alice knows U is equal to 0. So that's not the assumption C yet. It's just saying he makes the prediction what Alice will observe. But now we can use the fact that Charlie also knows that Alice is an agent. And remember what it means to be an agent. It's a information processing system that applies the same rules as Charlie would apply. So in particular, he can now simulate this reasoning that Alice did and say, if Alice saw 0, then she must have concluded that x is 0 bar. So he would actually conclude that still U is 0, but also that Alice made this conclusion x is equal to 0 bar. And now comes finally this assumption C in. C now tells him, but this means x is 0 bar. So at this point, Charlie only knows that Alice knows that x is 0 bar, but then by this consistency assumption, this must mean x is 0 bar. So Charlie can, in this case, conclude x is 0 bar. And now the last step of the argument is to consider Bob. So what can Bob say? Here we use now finally the whispering thing. So let's suppose, that's the assumption we anyway make, that Bob observed 1 bar. So Bob observed this. Now what can Bob conclude from this? Remember, this is something we evaluated when we considered the whispering. So let me bring that back. So we said if Bob has 1 bar, then z hat is equal to 0. So I just copy this. Now I can do the same trick as before. I can say what it actually means, actually for Bob means, is that he knows z hat is a value that is observed by Charlie, sorry. So remember, Charlie sees the value z hat. So the more correct way of thinking of this is, Bob concludes that Charlie's knowledge is that z hat is 0. But now he also knows, I will now do that in one step, because he can simulate Charlie, that Charlie came to the conclusion from this that x is equal to 0 bar. Now we can again use assumption C. And from assumption C, you can conclude that x is 0 bar. And this is now something he can say with certainty. So whenever I said, all these statements is to be understood, the probability of this happening when you apply quantum theory is probability 1. So Bob comes to the conclusion that with certainty, if the referee measures here, so remember this setup, if the referee measures here, he will get the outcome 0. So in other words, Bob can make a prediction with certainty. He can say, actually, you will measure here x equal 0. So he just sends that to the referee. Now, I will now not do that in detail. Now you have seen the reasoning, but you see it almost immediately if you want. We have before also said that, I mean, we have already used the fact that if you know here that the Q is or let me put it again from here. So Bob has already concluded that Z hat is equal to 0. So from that, he can also conclude more directly. So if Z hat is 0, then this means that this lab state will be 0. That's what it means, which means that if something is measured in the Z basis, we will get a 0 here as well. So this I now did very fast, but because you have now seen the way of reasoning before, I'm just mentioning it. So Bob can also reason that with the same assumption here that Z is equal to 0. So this means he can also make a prediction, he can also fill in the prediction here and say Z is equal to 0 with probability 1. So from Bob's viewpoint, he can make predictions for both possible measurements that the referee does, which means that Bob will predict that the game is won with probability 1. So that's now our conclusion. Bob comes to the conclusion the probability of winning the game is equal to 1. And to arrive at this conclusion, he used the assumption, the universality of quantum theory and the consistency. However, yesterday we saw that by purely applying quantum theory to just general thinking, I mean, Bob could also do that himself, he would also come to the conclusion that the complementarity game cannot be won with probability larger than 1/2 plus square root of 1 over 8. That's what we saw yesterday, which is strictly smaller than 1. Now this means that if you repeat this complementarity game many times, for sure you will lose at some point. So this here implies you win always win when you repeat, and this implies that you will lose after finitely many rounds. And this is something verifiable, that you can actually play the game and see whether you lose after finitely many rounds or win always. But these are clearly, so therefore these are contradictory statements about an observable thing, and that's the contradiction. So now you have seen the proof of why these assumptions Q and C, and Q is used again, lead to a contradiction. Yes?
Can the C assumption be a bit weakened?
Which assumption, sorry?
Yeah, the C.
C, yes.
Like weakened, like that other agents that they behave but not always perfectly.
Yeah, I mean, the weakening of the assumption is a very good question, and actually Lydia and I wrote a recent kind of reply to some, let's say, other work that questions the assumption C, where we discuss different ways of weakening. I think our conclusion, please correct me if you see this different, is that it's very difficult to find a weakening that is still, let's say, strong enough to actually collaborate in practical situations, because we still want to be able to talk, but still weak enough to avoid the paradox. You can somehow do things like, if you are in a weakness friend type situation, don't apply it. But as Ile pointed out, we don't know whether later someone comes and measures us in a, I mean, it's not even clear what that means, because what does it mean to measure something? Is if once I die and my brain content is kind of distributed as ashes somewhere, then what does it mean that the information is now not measured, or is it measured, and so on? So it would be very hard to make any of these things. But what I can say is that all assumptions are robust. So if you just weaken it in a way that say it's almost always true, in the sense of like with probability 0.99 from the viewpoint of some agent, then everything still works. I mean, works in the sense it doesn't work. It runs in, you run into the same contradiction, which is the worrying feature of this whole thing. Yes?
I want to pose two questions. The first is, can you show again the flow, the chain of...
You mean this here, or? Yeah, so you mean this is the experiment, and I had here the argument. Did you mean this?
Yeah, I mean the last line.
The last line here. The very last line. This I went very quickly, but okay, let me, as you ask, let me 5 minutes. Okay, then I can still explain it. So, okay, Bob. So, I mean, there is one subtlety here which has to do with the Heisenberg cut, and to make it precise, one would actually introduce an additional player who puts the cut a little bit different. And the subtlety is the following: that Bob, to make the predictions we did, has the Heisenberg cut in such a way that he can maybe I'll show it here. So Bob talks about the value set hat, which is measured by Charlie here. So if he talks about that value, he cannot see all of Charlie as a huge quantum system, because he has to decide, like, an agent should not change his cut, in a sense. So now, in order to do this final analysis, or this last line, I would want to still see these players as quantum. So I want to analyze this state here that describes Q and L as a joint system. And let's suppose if we do that, so you can think of a Bob prime who has chosen the cut a little bit differently. So what can this player Bob prime say? So Bob prime can basically do the same analysis that Alice did here and write down this state, if you like. And if you write down this state, you see from this version here, like, you look at this. So let's suppose Bob now looks at this state. And now, what was the statement? So he measures W equal 1 bar. So if he measures W equal 1 bar, then, it's actually even easier maybe. So the W measurement is on the Q system. And let's see. Yeah, so we can even look at that version of the state. So the W measurement is on the Q system. If you measure 1 bar, you know you are not in that branch, so to speak.
Yeah, but my question was, in fact, you said that the outcome 1 bar always comes up with probability 1.
No, I didn't. This was a misunderstanding. No, I didn't say that. What I said, okay, let me maybe briefly finish that. So there was this last line here. And the last line says, if Bob measures 1 bar, he concludes Z is equal to 0. So what I was now explaining is that, and I'll come back to the other point. So if he measures 1 bar, he knows he's not in that branch, because 0 bar is orthogonal. So he knows in that branch, but in this branch, the Z value is 0, which is also obvious from this description here. So if Z is equal to 0 and you proceed here to here, it will correspond to S being in state 0. And if S is in state 0, if you measure in the Z basis, the outcome will be 0. So that explains this last conclusion, why Bob can make this. Now your question is why, how do we know that the value 1 bar occurs? So what I said is that 1 bar, this outcome will occur with a non-zero probability, but not necessarily 1. And that's very easy to see. You just calculate the overlap between this and the initial state. So it's actually, I think, 1/6 or so, the probability of this happening. So you can just calculate the overlap of this with the initial state. But because the probability is not 0, you know that if you repeat, quantum theory tells us that if you repeat the experiment, we will at some point see the value. That's just basically what you can say. This is what the Born rule tells us. If probability is not 0 and if we repeat, then we get that outcome. So that was the reasoning. I didn't show that calculation, but it's a very simple one. I just don't want to do it because it's a bit messy here on that piece of paper. But if you're interested, I can show it to you afterwards. So, yes.
Another question, maybe, I don't know if this is more related to this. No, but we wanted to say only, because you talked about collaboration, right? But now they are not talking, right?
They are. They're whispering. That's what's the. So you see, this is a communication from Charlie to Alice. Yeah, that's why. It's not a classical. It's not a communication in the way you would typically model it as we talk here, because here I would say the communication works even if there's a lot of dissipation and so on. but it's a very well defined. It's a quantum communication. Charlie sends a qubit, encodes her. So Charlie has classical information. She then encodes it in a qubit channel. So that's something that we can actually do with today's technology. That's not something special. So we encode that. We actually even do it in daily life by optical communication. There we really have quantum states of light. And if you really optimize things, they are not necessarily even orthogonal, but you do error correction and so on. So she encodes that, and Alice just measures it, and again has a classical value. Now, in the particular case where Alice sees the outcome, let me come back to here. If Alice sees you, actually, let's now say Bob, for the purpose of, if Bob sees W equal to 1 bar, he knows even for certain what Charlie tried to communicate to her. The only difference to, let's say, the usual communication we do, if I ask you a question and you say yes or no, then even in the case when you say no, I'm sure you said no. It's a bit like the reason why we called it whispering is the following example. Let's suppose you, I ask you to check whether there's coffee outside. And please leave the room and shout yes if you see coffee. Now, if I hear yes, you shouting yes, I'm certain there is coffee. If I don't hear anything, it could be that the door is just isolating the sound so well that I didn't hear it, or it could be that indeed you didn't shout, so I'm uncertain. So it's a kind of asymmetric situation. So the only difference to the normal way of thinking when people say, oh, let's just open the box and ask Charlie what is your outcome, is that we now have an asymmetric situation. We kind of open it in one branch but not in the other. And that's the whole trick. That's very important for the working of this paradox. Otherwise, people always say, there's nothing you can do if you have a weakness friend situation to kind of decide what's going on, because either we open the box, you saw that also in the experiment that Jaslav presented, there it's of course resolved by doing this freedom of choice and making assumptions about the absoluteness of events and so on, but you could say, there either we open the box and ask, but then the coherence is destroyed, or we keep the box closed and we keep all the coherence, but we have no information about what's going on. Here we are reaching a middle ground, which exactly now suffices, as I showed in this argument, to reach the paradox. So it's kind of, we get just enough information to, in one particular case, namely if W is equal to 1, make a decision, and it's still weak enough, there's so little information that there's enough coherence left that we can somehow run into this paradox. I think that's really the main trick, this whispering, in a sense. Yes?
So, you talked about rejecting all the things that Bob doesn't get 1 bar.
Mm-hmm.
But if we weren't to reject in those cases, is the probability of winning with this strategy be greater than 0.86?
So I didn't understand the very last part. So, I mean, then it would be, yes, 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 yes.
But if we were to accept all the results possible and try to
Aha,
either way,
yes.
would we be above the 0.86 that we got yesterday, 1 half over?
Yes, yes. Yes, it would be above. But this is not, so because the game is set up in such a way that you can do anything you want for a preparation, you're in particular allowed to kind of just do stuff that in the first attempt fails. I mean, it's actually something we do all the time. If an experimenter calibrates his device, he would just move, maybe rotate his mirrors and so on until he sees what he wants, and then say, now let's do the experiment with that data. So in a sense, we are always doing that type of post-selection. The important thing is that we are not doing the post-selection during the game. That would be kind of a cheat. So we cannot say, now the referee told us in which space he measures, and we say, oh, in this case we don't want to answer. We kind of, once we start the game, once we send it, we don't no longer abort it. That's important. Otherwise, so we just have to do something that is provably impossible quantum mechanically. And if we abort before, or post-selects before, that's still impossible to win quantum mechanically. I think I should stop here now. Let me just give a reference at last, which is, this version of the thought experiment is described in this preprint that I've written together with Ladina recently. And this preprint also has another feature which I so far didn't talk about, but I mentioned it, which is that one can map these paradoxes almost one-to-one to paradoxes in quantum gravity about black holes, notably the so-called firewall paradox. And what you find is that the assumption C also appears there. But they have also gravity assumptions. So one can say that this result, that assumption C and assumption Q lead to a contradiction, is actually very relevant in gravity, because it tells you that if they have a no-go theorem that says Q, C plus gravity assumptions leads to a paradox, we cannot infer from that that the gravity assumptions are problematic. So in a sense, what this shows is that before you move to gravity and try to find paradoxes there, we should first clean up quantum theory and make sure we understand how agents collaborate. And this is particularly relevant in gravity, because in gravity you have necessarily different agents if you consider black holes, because you cannot see things from one viewpoint. You have one agent in the black hole falling in, one staying outside, and so they have to somehow collaborate. The outside has to send information to the inside, for example, and if you allow this collaboration, then you immediately run into these problems. So in other words, to even think about these gravitational paradoxes, it's necessary to first clean up our understanding of collaboration in pure quantum theory, which doesn't seem to be possible. But now our strategy in the future is still to learn from quantum gravity to maybe resolve the paradoxes, but that's a different story, and maybe I will talk about that in 2 years. Okay, thanks a lot.